So all the work we have done so far has been leading up to this, finding the polar form of a complex number. This is a different way to express those complex numbers, which usually we write as an a plus bi. It allows us to give them an angle and that absolute value, so we can start looking at things like symmetry on the complex plane. More on that later. For right now, we just want to be able to get comfortable writing that polar form. So in order to get our polar form, we're going to have our complex number z. We usually use z to represent complex numbers as opposed to x or y. So that z is going to have a couple components. It will have an r, and keep in mind r is just that modulus or that absolute value, that thing that we just found. And then we will also have two pieces. We are going to have a cosine of theta and an I sine of theta. If you're looking at that and suddenly going, oh no, trig is coming back, don't freak out. We're not talking about full-on identities and craziness here. When we're thinking about y cosine and y sine, well, our complex plane we usually think about as being analogous to our xy plane, where those real values are on the x-coordinate, the x-axis, and those imaginary values are on the y-axis. So when you're thinking about your xy points, something like that dot right there, keep in mind we use our cosine theta to describe that first coordinate, that x-coordinate, that real coordinate, and we can use our sine theta to describe that imaginary coordinate or that y-coordinate. If we were actually drawing in a triangle here, you could also think about these as adjacent and opposite, if it's helpful to think about them in terms of right triangles. So this cosine and the sine that we're talking about is the same cosine and sine that we've seen come back over and over and over second semester. Now they're just parts of the right triangle that build up that complex plane, that two-dimensional r and imaginary axis plane. So when you're looking at this cosine, keep in mind that is our real values on the complex plane, so it does not get an I. The sine, well, that's our imaginary values on the complex plane, our vertical ones, so it does get the I in that polar form. Note that r, that modulus, has been factored out. There is an r for both pieces. If we were going to look at this thing as a coordinate pair, that r gets factored out when we write the polar form, so it's sitting out front there. So it's an uglier looking version, but it winds up being very useful for a couple of things. One is graphing. The graphs here will be fairly quick, but it really is going to be about symmetry. When we start adding, subtracting, multiplying, dividing, taking square roots of these kinds of things, we'll be able to visualize that symmetry on this polar plane much better than we would on an xy coordinate plane. So let's just write a couple of these things out in polar form. Keep in mind there are going to be two things we need. We're going to need that r value, that modulus, and we will also need an angle, sometimes called an argument. So let's find those two things. Start with the modulus. Keep in mind that's just Pythagorean theorem. So to find that modulus, it's 4 squared plus a negative 4 squared. And then we're just simplifying. Well, 4 squared is 16. Negative 4 squared is 16. So that's going to be the square root of 32. 32 we can break down into 16 times 2. And the square root of 16 is 4. So that's going to be our modulus, our absolute value for this complex number. No big deal there. We also need to know an angle. So keep in mind, just like when we were converting from rectangular to polar in the past, we need to be careful when finding that angle because there is this deal about quadrants to worry about. If my real part is positive and my imaginary part is negative, that's going to be a quadrant 4 complex number. So when I go to find tangent, in particular, tangent inverse. When I go to find tangent inverse, again, we're talking opposite over adjacent, or y over x. So that's negative 4 over 4. What I'm really looking for is where is tangent going to be negative 1, because negative 4 over 4 reduces to negative 1. When we bounce back to our unit circle, there are a couple of places where tangent is negative 1. So we need to keep in mind the quadrant that this complex number lies in. Again, there is more than one representation for this complex number. You certainly could use that quadrant 2 angle, but it requires you to change the sign of your modulus. And we want to go ahead and stick with this version wherever possible. It is really nice when that modulus is a positive number. Keep in mind, absolute values, not supposed to be negative. So we really want to do our best to keep these things in standard form and actually use the angle in that fourth quadrant. So that's going to be 7 pi over 4. Swinging on back. So theta is 7 pi over 4. So putting this all together, I'm giving myself a little bit more room here. So putting this all together, our absolute value, our complex number z has an absolute value of 4 root 2. Again, that's coming from all of this work here. And then it has an angle. That's 7 pi over 4. We often call that angle an argument. So the argument goes into both cosine and into sine. So cosine of 7 pi over 4 plus I sine of 7 pi over 4. So you'll wind up using that angle twice. You wind up using the modulus only once. Last thing that we are asked to do is actually graph this thing on the polar grid. No big deal there. 7 pi over 4 is our angle. So 7 pi over 4 is along this line here. And we want to go 4 root 2 units in that direction. It's just like graphing those polar coordinates. So if I want to go 4 root 2 units in that direction, we can pull up a calculator to help us out here. 4 root 2, which is approximately 5.6. So right about, looks like each one of these tick marks is 4, so right about there. I'm going to get rid of this purple. It's probably difficult to see that point there. Right about here. So we can go ahead and do one more example of these, taking a look at number 11 here. It's going to have some slightly uglier numbers. Nothing we can't handle. So once again, we want to start with that modulus. So finding that modulus, that absolute value here, that's going to be the square root. Our numbers are going to be pretty ugly. It's going to be all right. The square root of negative root 7, quantity squared. And then we get a root 21 squared. So the square root of 7 times the square root of 7 is just 7. Negative times a negative makes it positive. So this whole thing will just be 7. Square root of 21 squared will just be 21. So when we go to put those two things together, we will get the square root of 28. Now root 28 is another one that we can break down. 28 is the same thing as 4 times 7. And the square root of 4 is something we can manage. The square root of 4 is just 2. So that takes care of our modulus. And I'll go ahead and make that green like we did in the first example. So our modulus is 2 root 7. We also need to find our angle, our theta, our argument for this absolute value, for this complex number. What direction is it going? So let's go ahead and do that. Theta will be tan inverse. Keep in mind it's tangent inverse of y over x because y is our opposite side. Tangent is opposite over adjacent. So we want that y on top and that x on the bottom. Don't want to lose that negative sign there. Root 21 over root 7. At first glance, oh no, that looks terrible, except we can actually simplify that. Not too bad. 21 over 7 is just 3. Positive divided by a negative will be a negative. So what I'm looking for is tan inverse of the opposite of the square root of 3. So before doing a unit circle lookup, we do want to double check our complex number here. Note that x is negative, y is positive, so this is a quadrant 2 angle. So we want to look for that negative root 3, but in the second quadrant. So negative root 3 in the second quadrant, got it, right here. Again, there's also a negative root 3 down in the fourth quadrant. We don't want to play around with that one. We want to make sure that we keep our modulus positive. So we want to take a look at the second quadrant angle, 2 pi over 3. And in keeping with the previous example, go ahead and let that be highlighted yellow. So putting this all together into polar form. In polar form, then, our complex number z. It's going to have the modulus 2 root 7. And then in parentheses, we will have cosine of 2 pi over 3 plus I sine of 2 pi over 3. Again, that 2 root 7, that's coming from our modulus. And the 2 pi over 3 is our argument, theta. Last but not least, we will go ahead and graph it. Keep in mind, 2 pi over 3, that is this angle right here. And how far that direction we want to go? Well, 2 root 7. Yuck. Let's run back to the calculator here real quick. 2 root 7 is approximately 5.3. So we want to go 5.3 units that direction. Once again, I'll get rid of that purple so it's easier to see. That's right about here-ish. So that is going from our rectangular form to our polar form. I will do one more example. The next one's going to require a bit more calculator work, so I need a full screen to work through that one. So definitely take a look at these. If you're having questions, please stop by tomorrow morning. Make sure you get those addressed, or you can always pop by after school. I'm here after school as well. But this is what we're going to be working with moving forward, that polar form for a complex number.